Hello, this is a chemistry video on temperature and rate. So I've been following the textbook Chemistry, the Central Science. This is chapter 14, Chemical Kinetics, which has to do with rates of reaction and such. So in this video, we want to introduce variations in temperature. In the previous videos in this chapter, we've pretty much assumed that the temperature is constant, or it's one temperature. So we want to introduce the idea of how temperature relates to the rate of reaction in this video. All right, hold on for the ride of your life. So basically, we assume what's called the collision model in figuring this out. Basically, the rates of most chemical reactions increase with temperature. Why? Because things are moving faster and there's more collision. So an increase in collision. So the assumption here is that a collision has to take place in order for molecules to react. So you don't have chemical reaction of two molecules that are hanging out on opposite sides of the room. It's only when molecules bam into each other that you actually get a reaction. And therefore, the assumption that molecules must collide to react implies that when you've got a higher temperature, and therefore you've got more movement, you have more collisions, and so you have faster reactions. Temperature goes up, faster reactions. All right, so there are three basic factors. According to this approach, there are three basic factors that shape the reaction rate. One is, as we've just said, the number of collisions per second. So more collisions per second, more faster reaction. That's the first one. The number of collisions affects the reaction. Secondly, the fraction of collisions with the appropriate orientation. So I'll talk about this in a second. It's kind of like how, if you're trying to shoot a basket, right? It does you wad up a piece of paper and you try to shoot it in the basket. If it lands outside the basket, there's no reaction. It has to hit the trash can, or if let's say basketball. You're playing basketball. It has to hit the net or the basket in the right place for it to go in. And so you're not going to get a reaction if the molecules don't hit each other with the right orientation. If they're not to where, oh, that fits just right. It's like docking to the space station. It's got to fit, or the reaction's not going to happen. It has to hit just right. And so, one, the number of collisions per second. The more the collisions, the greater the rate. Also, the higher the fraction of collisions with the right orientation, the greater the rate of reaction. The last bit is what we're going to call the fraction of molecules with activation, with the appropriate activation energy. You have to have a certain amount of energy, or it's not going to happen. And there's a diagram in the book. You ever played putt-putt golf? Where you got this little hill, and on the other side of the hill there's the hole, and you're on this side of the hill. You kind of gauge it. You don't want to hit it too hard because then it'll overshoot wherever you're going. But actually hitting it too hard, it's going to go over the hill. The problem is if you don't hit it hard enough, it might go up partially up the hill and then roll back down. You ever had that putt-putt? You start, you hit, and it actually goes off the court, off this, behind where you even started. Those are maybe irrelevant, but it's a picture. The activation energy basically says it has to reach the right amount of energy or the reaction's not going to happen. So those are the three things that affect the rate of reaction. How many collisions are happening, what fraction of that are happening at the right orientation, and what fraction has the right activation energy for it to happen. Okay, so first of all, the number of collisions per second. This is pretty obvious, but what you may not know is that only a tiny fraction of collisions lead to reaction. And the book uses the example of hydrogen iodide. In the formation of hydrogen iodide, only about 1 in every 10 to the 13 collisions produces a reaction. Think about that. That's a 1 followed by 13 zeros. Only 1 in that many collisions leads to an actual reaction. And so you can see that it's only the minority of collisions that actually results in a reaction. So first of all, the number of collisions per second increases the rate of the reaction. Second, the orientation factor. Molecules must be oriented in the right way during the reaction for a reaction to occur. I use the example of shooting a basket. If the ball doesn't hit the basket right, it's not going to go in. In the same way, the molecules have to hit each other just right, or the reaction isn't going to happen. So here's an example from, again, I'm sorry, I've not been creative. I've gone straight from Brown, Burston, LeMay, and Murphy's Chemistry of the Central Science. There's a diagram in there. So there might be, let's say that this molecule comes to this molecule, but it doesn't hit it right. Well, then you might just have it bouncing back as one green molecule. In the picture here, it does hit it right, and so it kind of sticks to this green one and it bounces back together. And so you see this had the right orientation, but you can see if it hit here, it's not going to react, or if it hits here, it's not going to react, or if it hits here, it's not going to react, or if it hits here, it's not going to react, or if it hits here, it might not react. It just has to hit it right in order for it to react. Molecules must be oriented in the right way for a reaction to occur. Sometimes there's an unstable intermediate state that a molecule has to go through, so it has to kind of get halfway. So like let's say you're trying to flip I don't know, those mailbox flags. You're trying to knock that mailbox flag up. So you're trying to hit it. You got to get it going, and maybe sometimes it's halfway, but once it's halfway, you're going. That's not a great example, but basically sometimes there's a middle shape to the molecule that it has to go through in order to get to the final product. We call that middle situation an activated complex. Complex activated, it's ready now for it to flip. It's halfway there, it's ready to flip now. Or a transition state. And I have a diagram from the book in a second. I'll try to make it clear what this activated complex or transition state is all about. So hold on a second if you don't understand the paragraph, because I'm going to come right back to it. Third, the activation energy. That's what we've been talking about here. The person that we have to thank or to blame for this idea of activation energy is Arrhenius. Svante Arrhenius. Obviously, he's Swedish. In 1888, he suggested that molecules need a certain minimum amount of energy to react. The activation energy. And it is E for energy with a small sub A for activation. Not very creative, but it works, right? So EA is the symbol for activation energy. So the rate of a reaction depends on the magnitude of this activation energy. In general, the lower the activation energy is, the faster the reaction. Why? Because you don't have to put as much into it, right? It's easier. It doesn't have to go up here. It only has to go down here. So the rate of reaction will go faster if it has a lower activation energy for the reaction. All right, here, remember I said I'd give you an example of the activated complex. So here we have potential energy. That's the potential for the reaction, and then we have the reaction pathway. So they use in the book this molecule here. This is methyl isonitrile, I think. Methyl isonitrile, I believe, is what this is. So this is a methyl group. So the methyl group's the same. Notice that both the beginning and the end have the same. So this is what's called an isomer. It has the same atoms in it. They're just in a different configuration. So this reaction is an isomerization pathway. We're changing one isomer to another. So EA, remember, not hee-haw, but EA is the activation energy. And so there has to be at least this much energy involved for this reaction to take place. And so this is a middle structure, the activation complex or the transition state. Notice that this is neither this nor this. It's kind of halfway. It's kind of wonky. The flag's halfway up. It's not all the way there. But it's close, right? It's like if you're rotating it, because that's what we're basically doing here, right? We're rotating the C in the end. It's halfway there. And so when it reaches the activation energy, it's halfway there. And now the C can connect to the other C, and we have the flip. And now this is called methyl... what's this called? Methyl. Oh, I'm forgetting what it's called. Anyway, it's acetyl. Yeah, methyl acetonitrile. So this is methyl isonitrile, and this is methyl acetonitrile. So that's what the activation complex is. It is now we've got it in the right position to just knock it the rest of the way. This is an exothermic reaction because it gives off energy. But this question, the question of whether it's an exothermic or an endothermic reaction is irrelevant. The reaction is going to happen once you reach the activation energy. All right, so a couple other things for this, this slide. So we have an equation for the fraction of molecules with an energy greater than or equal to the activation energy. So if you've got a mess of molecules, what fraction of all those molecules is going to have enough energy for that activation energy to happen? Here's the formula. So F, this fraction, equals E to the negative EA divided by RT. Now, you don't really need to understand what this is. This is a second, if you're watching this video and you're taking chemistry, you're probably in second semester chemistry. So you'll go deeper into these things if you ever take PChem or physical chemistry, which I've never taken, but I hope to one day. I hear it's very hard, but you don't need, it's more math and calculus based. But basically, what are these things? E, which we mentioned in a previous video, is a constant. It is 2.718281828 and on to infinity. It's an irrational number. It never stops, but it is a constant of nature. God likes this number, and so it's the natural log constant. Anyway, but anyway, e to the negative EA, that's the activation energy. R, if you remember R, that's the gas constant, 8.314 joules per mole Kelvin. So it's a constant that you should memorize before you're done with chemistry. And then T is the temperature in Kelvin. And so this formula will tell you, Arrhenius came up with this, I believe. This formula will tell you what fraction of the molecules are have sufficient energy for the reaction to take place. The answer is E to the negative activation energy divided by gas constant times temperature in Kelvin. All right, so you can see as the temperature affects this fraction. Okay, so that is general thoughts about activation energy. The last part of this section, it's a hard section, it's a long section, basically connects the constant that we've already seen, the constant in the rate of reaction. It tells us how to formulate that constant in terms of this fraction that we just talked about, E to the minus activation energy divided by gas constant times temperature Kelvin. So we just had that, this is F, right? E to the minus EA over RT. We just had that formula. It's the formula for the fraction of molecules that are ready to go. They're ready to go. What is A? A is another constant. A is sometimes called the frequency constant. It's not exactly constant. It does vary slightly with temperature and such, but it's constant enough for us to treat it as a constant. Now, what happens is if you take the natural log, and again, you don't need to know what the natural log is, you just need to how to press it on the calculator, but I do talk about it in the previous video. If you take the natural log of both sides, then we have the natural log of K equals, now what happens is, and we said this in the previous video, when you take the natural log of E to something, the E and the natural log disappear, and you're left with just the exponent. See, here's the exponent. So when we take the natural log of E to that, we end up with that. Negative activation energy over gas constant times temperature Kelvin, okay? And then plus, when you have two things multiplied by each other, it's a rule of logarithms that the logarithm of two things multiplied by each other is the logarithm of the one plus the logarithm of the other. So this natural logarithm of A, it comes from basically taking the natural log of both of these multiplied by each other. All right, you don't need to know how we got that, but this is what we end up with. We end up with this formula. And also, if we take this formula for two different temperatures, so K at temperature 1, K1 at temperature 1, and K2 at temperature 2, and if we then subtract them from each other, again, it's a rule. In other words, we do the natural logarithm of K1 minus the natural logarithm of K2. By the way, it's in the textbook if you want to see how the math plays out. I'm giving you the end result. So if It's another rule of logarithms that if you have logarithm 1 minus logarithm 2, that's the same as the logarithm of 1 divided by 2. So if you have the logarithm of k1 minus the logarithm of k2, that's the same as the logarithm of k1 divided by k2. And then this here is what you get when you play out the math of subtracting those. Why do I want to know this? Because what this now allows me to do with this formula in hand, I can now figure out what K is for something at a different temperature. So if I know temperature 1 and I know temperature 2, and I know the activation energy and I know the gas constant, and I know at least one of the constants, then I can solve for the constant at another temperature. And then I can use the rate laws that I've already talked about in previous videos. Basically, if I'm only missing one of these variables, then, and I know what the gas constant is, it's a constant. If I know all but one, I can solve for whatever's left, and that can be useful. All right, well, this has been a very torturous and difficult video on temperature and the rate of reaction, following chemistry, the central science.